Okay, dear friends, I think I'll start just a brief introduction, although almost everybody knows at NIMR and in India knows Professor Rosenthal, including, of course, Kailash Pandey, who used to work with Professor Rosenthal several years ago. So Philippe is professor in the Department of Medicine at University of California in San Francisco, and Associate Chief for Academic Affairs and Research in the Division of HIV, Infectious Disease, and Global Medicine at San Francisco General Hospital. So he's a clinician as well. At UCSF, he's a member of the Biomedical Sciences Graduate Program and Global Health Sciences Program. I think most of you know him in a more familiar fashion because he's the editor-in-chief of the prestigious American Journal of Tropical Medicine and Hygiene since 2014. And several of our papers, of course, have been reviewed and bettered because of his editorial capabilities. And he's also on the editorial boards of 4 other medical journals. He has served on review groups and advisory bodies for the NIH, WHO, and many other organizations. Professor Rosenthal's research, funded primarily by NIH, focuses on the treatment of malaria, including studies of antimalarial treatment and chemopreventive efficacy, translational studies of drug resistance, evaluation of antimalarial pharmacokinetics and thermodynamics, characterization of mechanisms of action of novel antimalarial agents, and antimalarial drug discovery. His primary research sites are in Uganda, Burkina Faso, and at UCSF, and collaborations are in place with a number of countries all around the world. So a very warm welcome, Professor Rosenthal. We were lucky to catch you today as opposed to tomorrow. And we really look forward to this talk from you. Thank you.
Thank you very much, Dr. Sharma. Can you hear me okay? A few things have gone wrong. I want to make sure you can hear me.
We can hear you. I can hear you clearly, and we can see your slides as well. And I suggest everybody can open their chat on the side in case there's any comments to be made in terms of if there's a problem with the sound or with the slides. So it's all yours.
Okay. Thank you. Thank you for that kind introduction. I shouldn't get too much credit since I somehow, I don't know how, got the day wrong for this call. And we got really lucky that Sachin called me 15 minutes ago and my phone was in my pocket, and we sorted this out and my slides were ready. So here we go. I've known many of you. I've worked with some of you mostly on more basic science areas, and including the great work that, as mentioned, Kailash Pandey did in San Francisco quite a few years ago. And that work continues in our lab, but our main focus, to be honest now, is more translational research, studying drugs and drug resistance in Africa, and that's what I'll be focused on today. And the real question, of course, that's so important for many of us is resistance to artemisinins and artemisinin-based combination therapies being seen outside of Southeast Asia, where it's obviously very well established. Figure out how to move my slides here. Not used to this. Okay, here we go. So, of course, as you all know, very brief introduction, as you all know, malaria is a major problem throughout the tropics, but in particular, as you see in the blues and red, as you see in the yellows and reds on this map, greatest transmission intensity by far is in Africa. Certainly has the. But if you look more closely, you'll see some greens and yellows in a few other places, and of course that includes a good part of India. So outside of Africa, India, some would argue, has the biggest malaria problem. And so the questions that we're asking in Africa are also very relevant in India. Just a little bit more introduction. The story of malaria over the last 20 years or so is a great deal of progress, but also continued challenges. Progress has included actual elimination in many countries, a remarkable achievement. And you see these numbers are a few years old now, but as of a few years ago, many countries were getting close with, as you see, 50 with less than 10,000 cases, quite a few with only a few dozen cases. And many countries declared malaria free, including remarkably China, just think it was a couple of months ago. That's the good news, but the not so good news is challenges, especially in Africa. So this figure shows the 10 countries with the greatest burden in Africa, and the country with the greatest burden outside Africa, which of course is India. In this brief snapshot between 2016 and 2017, only India saw an improvement with decreased cases. Every country in Africa, every one of these 10, had worsening over that year. So roughly, we saw quite good progress between 2000 and 2015, but things have flattened out and not much improvement over the last 5 years in sub-Saharan Africa, while things are still getting better in many other places. And I believe that is certainly the case in India. Again, looking at the same kind of information, we see improvements here with many countries with very few cases left. Again, this slide's a little bit old, but China already was down to 0 cases. And when a country has no cases for 3 consecutive years, they can be declared malaria-free. While in Africa, this is parasite rate, percentage of children under 5 with a fever who end up having malaria, and that percentage is over 50% in many parts of sub-Saharan Africa. This map is incomplete. They don't have data from every country, but the bright colors in the countries that are studied show you still a huge malaria burden in Africa. And so, of course, there's a huge worry that ACT resistance could spread or emerge in Africa, and the consequences would be enormous because the burden is so great. Here's where we are approximately now from the most recent WHO World Malaria Report. Malaria cases, not much improved the overall number over the last 20 years, but of course the population of the world has increased a lot. The population of Africa has increased a lot. So actually the case incidence has decreased a fair amount. So really no change between 2015 and 2020. Malaria deaths have improved a bit more, but it's still a huge burden, still about 400,000 deaths a year. Interestingly, the percent of deaths in children under 5 has decreased. So we're seeing more problems in older children. That's an important message in Africa. But the mortality rate, again, the population of the world is increasing. So while the numbers of deaths has decreased somewhat, the mortality rate has decreased quite remarkably. So that's good news, but still a big problem. And in India, pulled out of this report, about 5.5 million cases are estimated, about 7,700 deaths in 2019. So you all know this, malaria control requires prompt, effective therapy. Our main, I'm talking primarily about falciparum malaria today for obvious reasons, because I'm talking about Africa, and ACTs are certainly the cornerstone of our therapy for malaria. But we also use drugs for other purposes. Of course, chemoprophylaxis in travelers, intermittent preventive therapy. In Africa, that is the standard in pregnancy, and a variation on intermittent preventive therapy, seasonal malaria chemoprevention with treatment for malaria every month during the rainy season, has become the standard only in West Africa, where malaria is highly seasonal. And mass drug administration is another potential use of drugs. Control of mosquito vectors is very important, especially with insecticide-treated nets and indoor residual spraying of insecticide, but that's not the focus of this talk today. And of course, the malaria vaccine, we've been waiting for it for a very long time, and the WHO just approved the RTSS vaccine. That's very exciting. But we all know that's not going to solve our problem. We know it's a vaccine with only modest efficacy. So we still need drugs, and drug resistance remains a very big concern. I think you're all familiar with artemisinin-based combination therapy, short-acting artemisinin plus a long-acting partner drug. We'd rather have combinations with matched pharmacokinetics, but that's not available right now. So we're stuck with this, and yet works well. All of these are different ACTs, all using an artemisinin component that rapidly decreases the parasite load, but you see the artemisinins are only available for the 3 days of therapy. Very soon after the 3rd dose, the drug is gone from the bloodstream. Partner drug persists much longer. That mops up any remaining parasites, which is good, but it does lead for the potential of selection of resistance to the partner drug. We have worried for years about resistance to the partner drug, but of course, what we're dealing with now in Southeast Asia and probably elsewhere is resistance also to the artemisinin. The last drug on this list, really, to my knowledge, is really only an important regimen in one country, which is India. It remains an important therapy despite the fact that we know there's a lot of resistance to SP. But of course, I saw that Francois Nostin, who is not Indian, but is on the call, so I'm a little embarrassed telling this story with him on the call because he knows it much better than me. But a little over 10 years ago, it was discovered that parasites in this part of Western Cambodia had delayed parasite clearance, and they were in this initial study, critical study in the New England Journal, they were compared with infections from northern Thailand, which did not have the resistant phenotype at that time. And so this slide shows clearance of parasites, the parasite density in hours after initiation of therapy. There are two different regimens here, but the details aren't that important. These two lines here, can you see my pointer okay? If someone can just tell me, because I'm referring to my pointer, I want to make sure you can see it. You see the pointer?
No.
Okay, I know, because I have two screens. Now you probably see it. Yes.
Could you move it around?
All right, I can live without it too.
Yeah, you can't see it.
Okay. All right, I'm not so used to WebEx. Anyway, the blue and gold points show parasite clearance in northern Thailand. It was, as expected, parasites cleared within 2 to 3 days. But the red and darker blue show parasite clearance in Western Cambodia. And it took a few days longer for parasites to clear. They're still cleared. Some argue that resistance isn't the right word for this phenomenon. I like calling it delayed clearance, but resistance is an easy way to talk about it. So I'm happy with that term also. But this is the phenotype that was first well described in this paper and that we're worrying about now in other parts of the world. This is a very quick summary of where we are in Southeast Asia. This figure is about 5 years old, but it's still pretty accurate, except the red in the pie charts representing resistance has gotten somewhat worse in many areas. There's decreased efficacy of artemisinins, and even more recently, artemisinin-based combinations, their DHA piperacillin in Cambodia. That's manifest as delayed parasite clearance. We've learned that standard IC50 assays, as we use to evaluate drugs in vitro, do not identify the artemisinin resistance phenotype, but very nice work by a group in Phnom Penh developed the ring survival assay, which is an in vitro equivalent, an in vitro marker of artemisinin delayed clearance. And we'll be talking about that later in my talk. Again, very nice work by that group, same group, Benoit Witkowski and many others, showed that actually Benoit gets credit for the RSA, and Aria et al. Was the paper that showed that mutations in the K13 gene are associated and are clearly the markers for artemisinin resistance. I wrote at the bottom, seen so far only in Southeast Asia. We have seen K13 mutations elsewhere, but we really don't have real strong evidence yet for artemisinin resistance outside of Southeast Asia, until, some would argue, until the last couple of months in Africa. And of course, that will be a main focus of the talk. Just very briefly, I'm just touching on this. We don't have time to go into it in detail. Really nice work has also identified the mechanism of, we think, the mechanism of artemisinin resistance. There have been a number of theories, but it looks like convincing work, especially in the Birnbaum paper in Science last year, it looks like alterations in hemoglobin uptake due to mutations in the K13 protein lead to slower ring development as less hemoglobin is brought to the food vacuole, and that leads to artemisinin resistance. And as some of you know, studying hemoglobin degradation in the food vacuole was what my lab spent almost all its energy on some years ago. So very interesting. And there are interesting connections between hemoglobin degradation by falcipain and plasmepsin proteases and the action of artemisinins, but that's not our topic today. Big worry has been not only resistance to artemisinins, but resistance to partner drugs. And there's a lot there. A lot of problems have already been seen. Mefloquine artesunate had problems years ago, in part due to early artemisinin resistance, and probably in part just due to problems with mefloquine. Amidiaquine is a chloroquine-like drug with some resistance around the world, yet still works pretty well as the ACT, artesunate amidiaquine. Lumefantrine is a wonderful drug that still seems to have no obvious resistance around the world, though its activity does change somewhat with PFMDR1 polymorphisms, as many of you know, but not. It doesn't appear that leads to parasites that are truly resistant to lumefantrine, but that's a concern for the future. Piperacin is the most dramatic story with resistance, where resistance developed in Cambodia, parasites in Cambodia soon after artemisinin resistance developed, and that has led in the last few years to dramatic failures, with failure rates over 50% in some cases in parts of Cambodia. So really dramatic failures of DHA piperacin due to resistance. And as I already mentioned, SP is an old-fashioned drug, tried and true. It's got some nice advantages, but there's a lot of resistance around the world. Somewhat less resistance in India, and artesunate SP remains an important regimen. I think it's debatable whether it should be a regimen right now to treat malaria due to resistance problems. In other parts of the world, it certainly would not work due to resistance. So a big part of this talk is to ask the question, is there artemisinin resistance outside? Key K13 mutations have been seen elsewhere. I think you all know, but I'll mention quickly that there are many, many different K13 mutations, over 100 that have been identified, and these are propeller domain mutations, but only a fairly small subset are associated with resistance. Actually, I'll go into that in more detail later. Just to mention these quick data, I'll go into more detail when I talk about data from Africa. In Guyana, in South America, in an important study in eLife, a small number of samples collected in 2016, 2017 had the 580Y mutation, which I neglected to mention when I talked about Southeast Asia. This is the most prevalent artemisinin resistance mutation in Southeast Asia. There were a number of different mutations circulating, but 581 seems to have won out in Cambodia and surrounding countries. So the same mutation in Guyana, but not clearly associated with resistance. There haven't been many studies, and more recent studies, the limited studies I've seen, have shown lower prevalence of this mutation. So it doesn't seem to have really developed a foothold in Guyana, even though probably it would mediate resistance as it does in Southeast Asia. A similar story in Papua New Guinea. 580Y has been seen, but only in 3 samples total that I know of, and not clear if this is associated with resistance. Eastern India, I'll get to in the next slide, and then we'll talk a lot about Africa. I'm guessing that many, if not all of you, are familiar with these studies. I'm not an expert on malaria in India, but 2 very important studies, which are really the same study, but broken into 2 publications, were published a couple of years ago. The first in 2013, the next a couple of years later. Both showed small numbers of patients with persistent parasitemia on day 3 and delayed clearance by the ring survival assay. So both clinical artemisinin resistance and in vitro artemisinin resistance. And with either of these 2 K13 mutations, one of them already well known from Southeast Asia, but the other a mutation that had not been described before as associated with delayed clearance, 625R. that's seen in the first study, and the second where after a year, the studies had more detail to them. This was a short letter. This was a full paper. 12% of the parasites had a parasite clearance half-life greater than 5 hours, which is the marker for clinical delayed clearance. 15 patients with the strongest evidence for resistance had the delayed parasite clearance half-life, persistent parasitemia on day 3, and delayed clearance in the RSA. And all of those 15 had one of these 2 mutations. Very convincing results, but for reasons I don't fully understand, there is some controversy about these results, and I don't know of other groups in India that have seen a similar finding. However, more recently, there was very recently a publication showing also delayed clearance without K13 mutations, here with fairly high numbers of patients with half-lives greater than 5 hours and delayed clearance by RSA. So interesting where things are going. Again, some of you know more about the details than me. I believe there is no, other than these studies from West Bengal and without other evidence from that area of the country or any other, I believe so far things still look good. But this is, of course, very concerning that these studies did show what really looks like ACT resistance, or at least I should say Artemisinin resistance, and we will see what happens. This is my one slide to say there are other drugs coming. This is the MMV pipeline with many early leads and candidates. The number gets whittled down. Many compounds fail in drug development, unfortunately. The drugs that have made it all the way so far are just old-fashioned drugs or ACTs, not completely new compounds, but there are some novel compounds that are coming along, and probably within about 3 to 5 years, we will be seeing new drugs. But unfortunately, it's been slow. And at the moment, we have to rely on ACTs. So now we'll focus on our work in Africa. As Dr. Sharma mentioned, it's in these 2 countries, but most of what I'll be talking about, I think all of what I'll be talking about tonight is from Uganda. So I'm starting out very simply, so I apologize for those who, this is too basic, but we look for drug resistance in the field by doing clinical trials, of course. Clinical trials are definitive tests for whether a drug is working, but they're not exactly studying drug resistance. They're studying whether a drug is efficacious, and drugs can fail for multiple reasons other than resistance, but clinical trials are essential. But of course, they're hard to do. We can't do those that easily and readily. They're expensive, and our ability to do them is somewhat limited. We then do in vitro, or what we call ex vivo drug susceptibility assays. When we study parasites immediately out of a patient, we call it ex vivo rather than in vitro, but we're culturing parasites and looking for the ability of drugs to kill them. This is a direct marker of drug resistance. Very useful, but difficult to do. It cannot be done at that many centers, especially in rural areas, but it's where we put a lot of our energy in Africa. And then when we know what to look for, of course, easier than ex vivo assays is looking for genetic polymorphisms associated with resistance. However, this can be misleading. We don't always fully understand what we're looking for. And so the literature has a lot of reports of resistance based on certain SNPs that might not really be resistance. But of course, these are really valuable studies and essential for wide surveillance, because it's so easy, so much easier to look for genetic polymorphisms compared to the other 2 things on my list. But we have to know what to look for. And with some drugs, we don't know what to look for, but with artemisinins, thanks to the identification of K13 mutations, we do. So these are very old studies. This is where we were in Kampala, the capital of Uganda, in the early years that we were working there. Believe it or not, our first study was of chloroquine. This was about 20 years ago, and chloroquine was the standard drug, and we found chloroquine was placebo. 90% of patients failed. When we did genotyping to distinguish failure due to a new infection soon after therapy with a true failure that the original parasite infection recurred, it didn't make much difference for chloroquine. It failed horribly. SP and amidiaquine were quite a bit better, but not good enough as monotherapies, but combined, they were quite a bit better. And we did a fair amount of early work just before ACTs came to Africa, showing that amidiaquine SP was a pretty good regimen, despite the fact that it was two old-fashioned drugs. This never became an important treatment because ACTs came around, but it's gratifying to see that this has become a critical regimen for prevention of malaria in West Africa. And this is what seasonal malaria chemoprevention, which is now used very widely in West Africa in areas with seasonal malaria, is these two drugs. And despite the fact that they both have some resistance problems, they're working quite well. Relatively little resistance in West Africa, and they're effective enough that they have really important effects on malaria. And then these are the ACTs, where artemisinin, amidiaquine, and artemisinin working much better. And most of our failures, as shown by the blue bar, are recurrence, but not true treatment failure. True treatment failures were probably really 0%. Genotyping is not perfect in a clinical trial, but the ACTs work very well. Here's just one study showing the same results that Grant Dorsey led. The years fly, it's a long time ago. Amidiaquine SP working pretty well, but the two ACTs working better, and happily AL, artemether, which is the standard of care in Uganda and in most African countries, extremely well with only 1%. And again, that might really be 0% true treatment. So clinical trials show ACTs are working. But let's move some years in the future. This shows two versions of the older results from Tororo, a city with very high transmission intensity, and Kampala with a big city with somewhat lower transmission intensity. Sorry, this slide's a little difficult without a pointer, but if you look at the risk of failure, there were many failures because this is Africa, where children who are treated routinely get reinfected within the month of follow-up. So we saw many failures, but they were less frequent in the AL group. And if we looked at the adjusted risk of failure, it was close to 0. So drugs were failing because children were reinfected, but the drugs were working, they were eradicating the infection. Now we move to more recent studies, now already a little bit old, but about 7 years ago. These 3 studies led by Adoka Yeka in 3 rural areas of Uganda. And you see continued high risk of failure because these are areas with high transmission intensity, but the relative efficacy of the 2 regimens has switched, where now AL failures are more frequent than failures with ASAQ. And if we look at the adjusted treatment failures, we're seeing a small number of failures, but they're all in the AL arm. So I'm not sure these results are definitive, but they suggest that with changes over time, with some loss of lumefantrine efficacy, which I will show you in a moment, the relative efficacy of artemether lumefantrine is now somewhat worse than the efficacy of ASAQ. AL has other advantages. It's still the standard of care. It seems to still be working well, but this is a little bit of a hint that problems may be coming. This is another more recent trial, 3 other rural sites in Uganda, now with artemether lumefantrine compared with DHA proparaquine. DHA proparaquine, as I just mentioned, a failed regimen in Cambodia, but still a highly efficacious regimen in Africa. And you see it working very well. And if you look at the, wish I had my pointer, if you look at the graph on the lower left, lower right, you know, clinicians have trouble with right and left because we're used to looking at x-rays. I guess this is the right on the slide. You see that the 2 drugs both work well, but recurrence after treatment is much lower with DHA proparaquine. And that's easy to explain. Proparaquine has a much longer half-life than lumefantrine. And this is why DHA proparaquine is a very promising drug for prevention of malaria. Some experts do not like the idea of using an ACT for prevention, but if you are going to use one, DHA proparaquine is always the best because of the long half-life of proparaquine. But of course, as I mentioned, we have already lost DHA proparaquine in Southeast Asia, which is concerning. And of course, that may occur elsewhere. Now let's talk about ex vivo. We set up a laboratory in Tororo, Uganda, near the Kenyan border, a little over 10 years ago. And of course, I know groups are doing this in India and around the world, but it's rather labor intensive and expensive activity, so not so easy to do. We are doing this in Uganda. We have been doing this in Uganda routinely for about 10 years, and quite recently have gotten, just this year, have gotten our system up and running and working well in Bobo Dioulasso, Burkina Faso. This, of course, allows us to study trends over time and to look for associations between phenotypes and genomes. So here's routine results, the compilation of many results over a few years at our lab in Tororo, Uganda. The y-axes are very different on this slide. Some of them are log and log axis. Some of them are showing log scale and some are not. You see that for most of these drugs, the range in activity is really quite narrow. Look, if you look at atovaquone down on the bottom, it looks like a wide range until you realize the least sensitive parasites are still showing an IC50 of 2 nanomolar. So most of these drugs are working really well. An exception is chloroquine. This is where we've been in chloroquine over the last 3 years. With a log scale, you see that most of the parasites are highly sensitive. The yellow dot is 3D7, a sensitive parasite, but a subset of parasites are resistant with, I think most would consider an IC50 above 100 nanomolar to be chloroquine resistant, and the blue dot is DD2, a known chloroquine resistant parasite. So in Uganda right now, we're seeing a minority of parasites still resistant to chloroquine, most sensitive, but good activity of pretty much all the other drugs I'm showing you on this slide. But are things changing in Uganda? And of course they are. I wouldn't be talking about it unless there have been changes. And there have been dramatic changes, as I was just alluding to, dramatic changes in chloroquine. With the IC50 in our earlier studies, about 2010 to 13, median IC50 is well over 100 nanomolar. Now we're seeing the median more like 20 to 30 nanomolar. Similar dramatic improvement in monodecyl amidiaquine, the metabolite of amidiaquine. Improvement also in piperacquine, though the difference is much smaller. This is not a log scale. And interestingly, some worsening of the activity of lumefantrine. We understand why that is, as I'll get to in a moment. It's a relatively small difference. I don't know if this explains the difference in AL treatment efficacy that we have seen over time, because this is a very small difference, but nonetheless, it's a statistically significant difference seen consistently in a number of studies. And IC50 assays are not really the right way to identify artemisinin resistance, but for what it's worth, we see no difference in DHA IC50s. What about the genetic polymorphisms associated with resistance to these drugs? For PFC and PFMDR1 mutations that are the key mediators of resistance to chloroquine, we see dramatic changes over these 10 years. From most parasites being mutant, some mixed, we see lots of mixed infections in Africa, and just a small number wild type. Now, 6, 8, 10 years later, nearly all parasites are wild type. This is not, of course, a story only seen in Uganda. It was described in Malawi some years ago because they stopped using chloroquine earlier than other countries in Africa, and has been seen in many countries in Africa. The other main mediator of resistance, the secondary mediator, is the 86Y mutation in PFMDR1. And you see also, we've just about totally lost this mutation. If we had gone back a few years earlier, almost all parasites were mutant. Now almost all parasites are wild type. So consistent with the ex vivo results that I show, that are down on the bottom that I showed you on the last slide, activity for chloroquine and monodecyl amidiaquine has gotten better, and for lumefantrine has gotten worse, which is explained by these data with the wild type of 86Y being associated with somewhat less activity of lumefantrine. So the genotypes and phenotypes make complete sense here. But has chloroquine resistance disappeared? I guess I already answered that question. Not quite. These are now results over time, and we're still seeing some parasites above this 100 nanomolar cutoff for resistance, not many anymore, but some. And most of these, of course, an ex vivo assay is a difficult assay. There could occasionally be spurious results, but most of the isolates that are above 100 nanomolar have the K76T mutation. Again, that's consistent with the results I showed you on the last slide. Patrick Tumwebaze, who's been working with our group for a long time in Truro, put together these slides showing the progression all the way in these same polymorphisms, PFCRT and PFM1, all the way over the last 20 years from 2001. You see that long ago, this is from many studies. Many of these are from our group, but not all of them. Some are from other groups. 76T was between 2001 and 2010 or 12, virtually all mutant. 86Y starting to decrease in that time frame. This was a study we did over, well, it's a combination of a couple of studies we did over 5 years. And you see the impressive decreases. And now where we are now, this was 2018, 2019 in gold and blue. 86Y has just about completely disappeared. 76T has not yet completely disappeared, but it's getting there. So we're seeing the loss of chloroquine resistance. You could probably use chloroquine fairly successfully to treat malaria, though if we started using it regularly, it's very likely we'd select for resistance again. Now let's move to anti-folates, of particular interest in India because SP is such an important drug. This is where we were a few years ago. There's basically very high level resistance to, very high prevalence of 5 well-described mutations, 3 of them in DHFR, 2 in DHPS. I won't name them. The red, I'm using a pointer, but I don't think you can see it. But the 5 graphs that show all red are showing all mutant parasites with those 5 mutations. That's a done deal. We know we have these 5 mutations, but of great concern is the beginnings that we're seeing a few years ago in mutations to PFDHFR 64L and DHPS 581G, 2 additional markers that lead to very high level resistance to anti-folates and to SP. And what we recognized in studies a few years ago was a hotspot of resistance down in southwestern Uganda, right next to an area of the Democratic Republic of Congo, where a group that we now collaborate with, Ozidamir in Jeff Bailey's group, that time he was at University of Massachusetts, showed high prevalence of 581G in this part of DRC, right across the border. Not surprisingly, we're seeing the same thing. And I show that here, but I'll show it to you better on the next slide. This is the more recent study that Victor Asua, who's led most of these studies in the last few years. Victor goes around the country now to 16 different sites, which you see here in this graph, and looks at the prevalence of polymorphism. We'll be looking at this for K13 in a moment, but for the anti-folate mutations, again, very high prevalence of these 5 mutations, nothing new. This one mutation is lacking in most West African parasites, and it's probably why SP still works better. I'm sorry, the one mutation is 540E. I will continue to forget that you're not seeing my pointer, but the 540E mutation, not seen in West Africa, probably explaining why we still do pretty well with SP to prevent malaria in West Africa. But these are all high prevalence in Uganda. And in addition, we're seeing high prevalence of 164L and 581G in the areas on the maps that are getting more dark brown and red. And showing here, this is Kabali down here. I won't go through all the names of regions of Uganda, but you see high prevalence of 164L and 581G in 2018 and 2019, primarily in southwestern Uganda. And now to the question of Artemisinin resistance. We've already talked about this, so to move on. We briefly discussed K13 mutations, but now I'll go into a little more detail. There are over 100 different mutations seen in the propeller domain. Most of them do not appear to be associated with ART resistance, though of course for many of them, they've only been seen rarely and they haven't been studied. But there are specific WHO definitions for mutations that are relevant, and they're described as either validated when they're associated, clearly associated both clinically and by RSA, and that's these, what is this? I think it's 9 mutations, 3, 6, 10 mutations that are validated, and then others that are candidate or associated, which the data are not as convincing, but in most cases, the data are not as convincing primarily just because we don't have as many parasites to study. What I'm circling here are the key mutations we'll be talking about. We've already talked about 580Y, which is clearly the dominant mutation in most parts of Southeast Asia that have Artemisinin resistance. 561H is the mutation that has popped up in Rwanda in recent years, and the other two, 469F or Y and 675V, are the mutations we've seen in Uganda. So interesting stories from Rwanda showed that the 561H mutation was seen in up to 20% of isolates from 2 sites, Masaka and Rukara in central Rwanda. And sorry, this is where I didn't quite finish my slides for this talk today, so I don't have the references, but these are Uwamaya et al. 2 important papers that have come out in the last last year. And in the most recent paper, which I think was in Nature Medicine, but I might have that wrong, the 561H mutation was also associated with clinical delayed clearance, very convincing results. AL still worked fine for treatment when you used it with a full course of AL and you did the usual 28-day treatment efficacy study. AL worked fine, but a good percentage of parasites had delayed clearance. This is the most convincing evidence, the first really convincing evidence from Africa that we have a K13 mutation that is associated with delayed clearance. And as you see from these pie charts, the red here is the 561H mutation. It's the prevalence is quite high. Now, our work is in Uganda, just above Rwanda on the map. And so we're very concerned about 561H spreading to Uganda, but that's not what I'm telling you about today. We've seen only, I believe, 2 isolates out of a few hundred that have had the 561H mutation. It's other mutations we've seen in. So here's our story from northern Uganda. First, there was a study published by another group that worked in Gulu up here in northern Uganda at the end of that arrow. And they had a very small study in emerging infectious diseases a few years ago that showed that 4 of 194 isolates they studied with the ring survival assay, they were culturing parasites in Gulu, 4 of 194 had an abnormal ring survival. That is, for those of you familiar with this assay, you culture parasites just for 6 hours with a very high concentration of DHA, remove the drug, continue culture for a total of 72 hours, and then see the percentage survival compared to controls. And they used as their cutoff 10% here. The exact cutoff is not clear, but anyway, using the 10% cutoff, 4 parasites out of 194 had an abnormal RSA. 1 of them had 675V. The others had wild type K13. These results by themselves were hard to make sense out of. It was just 1 parasite. Hard to know what it means. But meanwhile, we were noticing that mutation plus another mutation in parasites also from northern Uganda, not too far away, especially these districts, Lamwo, Agago, and Kole. You see a few parasites in, this was 2017, a few parasites with the mutations, especially from Lamwo here you see for 675, and a few mixed or pure mutant with 469Y. So a hint of something. Combined with this study, this made us a little nervous. Victor Asua continued to collect parasites every year. This shows the results that I showed you previously from 2017, but now from 2018 and 2019. Now at 16 sites, we were previously doing 10 sites. And here's a map, just like I showed you for the anti-folates. But of course, it's not southwestern Uganda. It's north and northeastern Uganda, where you have the darker colors on our maps, with prevalence up to 20 to 30% at a few of these sites. The numbers of parasites are fairly small that we're studying, so the confidence intervals are large, but nonetheless, there's clearly something going on with, interestingly, two different K13 mutations seen at higher prevalence in 2018 compared to earlier data and at even higher prevalence in 2019. We now have partial results for our 2020 samples, and they look pretty similar to this, but there seems to be some spread with higher prevalence at additional sites around the country. The ring survival assay I already described to you, and I think because we must be running behind after all the problems we've had, I'll skip the details on the ring survival assay, but it's our standard laboratory assay for delayed clearance. What we did recently is decide we had to get parasites from northern Uganda, but study them where we could easily study parasites at our lab in Tororo. The group in Gulu had their lab at the right place. We did not. Our lab is where we don't see many K13 mutant parasites. So heroic folks in our group during the pandemic drove about 5 hours up to Patango, spent the night, collected parasites the next morning. There's malaria there every day, and brought the parasites back. And we've studied about 60 samples from Patango with the ring survival assay in Tororo. And these are very preliminary results. Melissa Conrad in our lab has played a key role in analyzing the results. They are not ready for prime time, but I'm sharing them with you. Compared to wild type, the parasites with either of these mutations, we don't have too many mutants that we yet have RSAs on, but they do have a significantly higher ring survival. However, we do see a few wild type parasites with very high RSAs. So we have a lot of parasites that are still pending. I'll have clearer results in about a month, I think. But it does look like the mutants are associated with delayed clearance. As you'll see in a moment, we also have results now from the group in Gulu. This is a very curious result that I don't want to believe because I didn't expect it. It doesn't make sense. But we have seen that the parasites from northern Uganda, from Patango Health Center, fairly often have high lumefantrine IC50s. Lumefantrine is a particularly hard drug to study in the ex vivo assays, probably mainly because of solubility problems. And so you sometimes see people publish lots of very high IC50s or lumefantrine, and I tend not to believe them because it's easy to get this assay wrong. But in this case, we were doing these assays side by side. Every day we had some parasites collected in Tororo, some collected in Patango. I think we know how to do these assays, and it does look like we're seeing some loss of lumefantrine in addition to loss of artemether in northern Uganda. Very concerning, but as I said, these are very preliminary results, so I don't want to make too much of it yet. Then, as many of you know, this dramatic story, well, dramatic because it's in the New England Journal of Medicine, this well-publicized story came out just a few weeks ago. The group from Gulu had done a clinical study, a somewhat unusual study, in that they treated patients with intravenous artesunate, even though they didn't have severe malaria, but that allowed them to do a clean study looking for delayed clearance, and they found clinical and in vivo artemisinin resistance associated with these same two mutations. They didn't have many 469Y mutants. They did see association with clinical delayed clearance for both mutations, only with the 675V mutation for the ex vivo result. These are additional data, but they're basically showing the same thing. And again, I realize we're running a little bit behind. But this is the story that has emerged over the last year to 2 years, that there are multiple different K13 mutations now circulating in Rwanda and Uganda that are associated with delayed clearance. So I'm being cautious because this is such an important conclusion, but I think the data are pretty convincing that we have artemisinin resistance now in East Africa. So is there artemisinin resistance in Uganda? As I said, the efficacy of leading ACTs, as far as we know, has remained excellent. It has remained excellent in recent trials, but more trials are greatly needed. Recent abnormal RSAs and the new clinical studies suggest some loss of ACT efficacy. And the spread of K13 mutations is worrisome. As I said, it does look like these are spreading around Uganda somewhat so far. And we have samples from 2021 collected a few months ago that haven't been sequenced yet. We're also concerned about worsening anti-folate resistance. Those extra mutations probably making SP worthless for malaria, even though it is still the standard of care for intermittent preventive therapy in pregnancy right now across Africa. And perhaps some loss of efficacy of lumefantrine. We'll see how that sorts itself out. So I'd like to thank a great many people who've been involved in all different ways with these studies, including our team in Truro. And actually, most of these people have worked in Truro and don't have time to mention them all, but thanks to a great many people. And I'll just mention quickly that we do have some postdoc opportunities available. We had great success with postdocs from India in the lab between about 10 and 20 years ago, a few since then, but not many, and we'd love to have more. So I'll leave it at that, and I'll be happy to answer questions. Sorry for the technical difficulties.
Many thanks, Professor Rosenthal, and I really appreciate that despite of your, you just came back from your vacations and the confusion between the time slot here. Thank you very much for your time today. And so the first question I would like to take from Dr. Kailash Pandey is here. And so I request him to start with the questions.
Yeah, I don't see Kailash, but oh, there he is.
He's here.
I had to move the little thing with the photos. It's good to see you, Kailash. It's been a while.
Yeah. So hello, hi Phil. So yeah, looking the same. You're a little bit more gray hair, but yeah, you are looking.
He said this to me by email a few days ago, and I answered a lot more gray hair.
So yeah, it's a great talk. So as you know, we have some potent inhibitor for 16 protease, but but I'm afraid we cannot use them in like combination because look to the mechanism of this Artemisinin. So this facilitated by these hemoglobin facilitate the action of Artemisinin. Look like so that is our concern. Like in spite of having good inhibitor, but we cannot combine with Artemisinin. Is that right or?
Yeah, I agree with you. I hate to say it. As you know, we put a lot of energy into cysteine protease inhibitors through the years, though none of them are, no protease inhibitors of any type are antimalarial drugs yet. But I think very nice work, mainly from Leanne Tilley's work, group in Australia, has shown that if you inhibit cysteine proteases, you decrease the activity of artemisinins, and presumably that's because they need hemoglobin breakdown to be active. And again, the K13 mutations in a completely different way are also preventing access to hemoglobin, and so decreasing activity of artemisinin. So yeah, I think cysteine proteases may still make sense as drugs. I hope they are developed as drugs, but it wouldn't make sense to combine them with artemisinins. I agree with that.
Okay, next question is, there are some reports of there are some reports of plasmapheresis 2 repeats and PMFDR1 mutants in Africa. How does this correlate with the resistance to DHA piperacin in field isolates? And what would be its impact on use of DHA piperacin in Africa?
It's a good question. I know that there was a report from Didier Menard's group showing increased plasmepsin copy number in parasites collected in the same place where we work in Truro, Uganda. It was a study done at the same site, but we were not involved in the study. And even though Didier Menard's group developed the assay, I still would argue that those results are not correct because we have not seen increased copy number of plasmepsin 2 in many samples studied from that area. And around Africa, I think the evidence for increased copy number of plasmepsin 2 and PFMDR1 is very limited. I'm not saying there are no parasites with increased copy number. Parasites are always experimenting, and they often change copy number of genes. But it doesn't seem to be a problem right now. DHA piperacin efficacy is excellent. We have extensively studied it also for prevention of malaria in pregnancy and children, and its efficacy is remarkable. 96 in one study in school children, there was a 96% decrease in the incidence of malaria with DHA piperacin. So right now, I am still a big believer in DHA piperacin in Africa. That, of course, could change. And some would argue we shouldn't use the drug for prevention because we want to save it for treatment. I would argue if we can prevent large numbers of cases of malaria, we should use the drug. But that's an interesting debate we can have. But again, those copy number changes, to my understanding, are not a significant problem in Africa yet, as far as I know.
Okay. One more question is, like in bacterial infections, observations for reversal phenotypic resistance and drug susceptibility are reported. Are similar observations seen for Plasmodium?
I have to say, I didn't understand the question.
Like in bacterial infections, observations for reversal phenotypic resistance or drug susceptibility are reported. So the similar observations seen for Plasmodium also?
I'm just not familiar with the terminology. I'm sorry. But by reversal, are we talking about a mutation having different impacts on different drugs? Is that, I'm not sure if that's what the question is asking about. Whoever asked,
this is
clarify.
This is also not clear in the question.
I'm not a bacteriologist. I'm not sure what reversal means in that context.
Okay.
Sachin, you should ask that Rahul's question. That's
yes. Down. So this is, could we accurately estimate the rate of decrease of resistance to previously administered drugs such as Chloroquine, so that they can be put again into future usage?
Yeah, that's a good question, and of course this gets discussed fairly often. There is an interesting difference between chloroquine resistance in Asia and chloroquine resistance in Africa that I don't think anybody understands, but is presumably mediated by the genetic backgrounds of parasites. In Africa, when you remove chloroquine pressure, parasites revert to wild type pretty quickly. Quickly being over a few years. That was seen first in Malawi in the 1990s, and now in Uganda, Kenya, Tanzania, and I believe across Africa. So you could argue if you really remove chloroquine from the scene, wait 5 years, you might be able to use chloroquine. As I showed you in Tororo, we're not quite there yet, but we are heading in that direction. But I think the worry is that there is so much. First of all, chloroquine, you probably can't completely remove it, especially now that the former president of my country told everybody to use chloroquine for a different reason. I apologize for that, President, but it wasn't my decision. If I'm allowed to talk politics, but chloroquine's around, so I don't think we're going to get down to zero. And in Asia, for whatever reason, and some of you know this well. When you stop using chloroquine, and chloroquine's been, not used in Asia in parts of Asia with malaria for many, many years, the chloroquine-resistant parasites are more persistent. So that strategy probably would be less effective in Asia. The other problem in Asia, though, and maybe the explanation for this, is that there's a lot of P. vivax malaria, and so chloroquine is still being used for P. vivax. That's less of a concern in Africa. So theoretically, we could go back to chloroquine, but I think practically, it will be very hard to do so, but hopefully we'll have better drugs. I mean, there are chloroquine analogs like AQ13 and others that may, work better against chloroquine-resistant parasites, but still give us the benefits of, what a good drug chloroquine was through its good years.
Yeah. So, yes, please go ahead.
Yeah, Phil, I have a quick series of 3 questions for you. I hope it's not going to run over time for you. The first one is in Uganda, for example, or other few examples that you showed with potential for Artemisinin resistance in Africa. Are those regions high transmission areas for malaria or low?
Yeah.
Or
good question. I think all of us have tended to say through the years that resistance tends to develop in low transmission areas, such as Southeast Asia. And there are logical reasons for that. Lower host immunity etc. But that's not the case. These are high transmission areas. Compared to most of the world, all of Uganda is very high transmission. But even within Uganda, those areas in northern Uganda are quite high transmission areas. It's not, southwestern Uganda is lower transmission because it's mountainous, but these are high transmission areas. I cannot explain why these were the sites where this resistance developed. There are a lot of refugee camps in northern Uganda due to problems in surrounding countries, but that doesn't really explain things. I don't know why these mutations developed in northern Uganda.
Right. No, that's very interesting. I think something for us to discuss later. I have two small questions. Very quickly, your views about TACT, the triple Artemisinin combination therapy.
Yeah, the groups in Southeast Asia, including Francois, who's on this call. I'm not sure who's on this call, so I have to be careful what I say. But I'm not worried about what I say for this because I think TACT is a very promising strategy. Of course, it's not so original. We treat HIV and TB and various other infections with many drugs, not just two. I mean, we treat TB with 4 drugs typically, and HIV often with 4 drugs. And it makes sense, and it's more than just 3 drugs compared to 2. It's, as you know, the regimens used in TACT are designed to give you 2 drugs with opposing effects on resistance. As you know, I didn't say this too clearly in my talk, but the same mutations that cause resistance to amidiaquine make parasites more sensitive to lumefantrine and vice versa. So regimens that combine these drugs would make sense to decrease the likelihood of resistance. Plus, of course, you're hopefully starting out with parasites that are fully sensitive, and you hit them with 3 drugs rather than 2, the likelihood of resistance to multiple drugs is very low. That's the positive, and I think we might see TACT very soon in Southeast Asia. I'm not directly involved in what's going on there, but it's a very logical approach, and the papers have been published. It seems to have stood up to scrutiny very well. However, the harder question is whether we should use TACT in a place like, say, West Africa, where there's no important problem with resistance to a number of different ACTs right now. It's probably going to be very hard to convince public health authorities to switch regimens to something that will be a little more expensive, more complicated. It won't be that easy. So I think it's a strategy that makes sense, maybe even makes sense for Africa, but will probably be a harder sell in Africa than it will be in Southeast Asia.
Right. And another very brief question, because it's so much in the news, the RTSS that's WHO approved, and you mentioned at the outset of your talk. What are your views about it? I understand, obviously, that it's essentially for the moment approved in Africa, etc., to prevent mortality in children, for example. But what are your views about its deployment where both PV and PF are endemic, for example, in most of India?
Well, first of all, as you know, I'm not the expert on vaccines, and some of you on this call are more expert than me. But of course, I've been following this for many years, and RTSS has been developed very slowly, in part because it doesn't really work that well. It's much better than nothing, but most vaccines, of course, vaccines are very much in the news right now also, but forgetting COVID, just vaccines in general have very high efficacy, and a vaccine that has 30 or 40% efficacy is not very convincing. Yet, looked at another way, if we could decrease malaria by 30 or 40 or 50%, that's a lot of cases of malaria. So it is exciting that RTSS has made it to the finish line. My understanding is deployment is going to probably take some years, just due to the difficulty of producing the amount of vaccine that's needed for Africa to start with, but potentially for other parts of the world. But it's not going to solve the problem. And my big worry about RTSS is that it will lead to some policymakers backing off on other approaches that actually work. Bed nets and indoor residual spraying of insecticide are really important strategies in Africa. better use of drugs makes sense. We should be using drugs to prevent malaria more than we do right now. That's my opinion. And I'm worried that the vaccine will cause people to back off on the other strategies because they think a vaccine will solve the problem. If we don't do that, having the vaccine as one of our tools, I think can only help. And there is even the interesting strategy of using, RTSS as part of seasonal prevention, what they now call seasonal vaccination. That was another paper recently in the New England Journal. That could be very exciting, but it's only one tool, and that's how we should think of it. It's a tool that's going to decrease malaria somewhat, as is the case with the other things I just mentioned.
Right. Yeah, thank you, Phil. From my side, Sachin.
Yes. So in continuation of the first previous question is malaria health services across the 16 sites you mentioned across Uganda, are they similar? For example, ACT coverage particularly higher in some sites than others. What are the factors that could have caused?
That's a good question. I don't think there isn't an obvious answer. There isn't an obvious difference that would explain differences in resistance that have emerged. These are all government clinics where malaria is treated with artemether lumefantrine. They do have stockouts from time to time, but in general, treatment is available. They're pretty good at, nowadays, not so much 15, 20 years ago, but nowadays quite good at diagnosing malaria with either RDTs or blood smears and treating appropriately. Obviously, drugs are probably misused a fair amount with people not taking the full 3-day course, but I don't see that would be different at different sites around the country. So it is true in Uganda, a small number of districts, about 10% of the districts get indoor residual spraying of insecticides because the country cannot afford to do it everywhere, and it's somewhat haphazard which places get it, and those places do better. But none of that explains why we've seen those resistance markers develop in two markers develop in northern Uganda, another marker in the middle of Rwanda. Can't really explain that. Right? It may just be chance, but once a mutant parasite gets a foothold, it has the selective pressure of mostly artemether lumefantrine, and that will allow, once it is fit enough to be propagated, it has the selective pressure of the drug to allow it to spread. That, I think, is what of course has been seen in Southeast Asia with a very complicated competition between many different K13 mutant parasites. And it appears we're seeing the beginnings of this in Africa, which is concerning, of course.
Okay, there's one recent study revealed that the fitness cost of ART resistance mutant from Africa is very high, thereby limiting a probable spread of Artemisinin resistance. So, if such data exists from the Uganda, is the question?
Not yet. We are just beginning studies, and some of these we're doing in collaboration with my good friend David Fiddick from New York. And David's lab has really nice recent data showing just very complex results for the impact of K13 mutations, both on Artemisinin resistance and on fitness. Clearly, the background of parasites is very important. We have very early data, and this is from David's group did the transfections, that transfecting these two mutations that we saw in Uganda into one Ugandan strain and into DD2 had relatively small impact on RSA results. That was a bit of a surprise. But his work with other K13 mutations, including 580Y and others that are common or were previously common, is that the results vary quite a bit depending on the background of the parasite. So there are K13 mutations that have a very strong impact on fitness and some that don't. I remember a paper from David's lab a few years ago that suggested that 580Y wasn't particularly fit compared to some other mutations, and yet the natural experiment has happened in Southeast Asia, and 580Y clearly has won out over other mutations. So clearly it was the most fit in a true biological context. And obviously our lab assays only partly replicate what really happens. So lots of, almost always, antimicrobial resistance comes at the cost of fitness, but when the fitness deficit is not too great, the selective pressure of drugs allows the resistant parasites or the resistant bacteria to emerge. And obviously that's what's happened with drug resistance in malaria for many years with many different drugs. But we need a lot more of this, and I can predict that the recent stories from Africa are going to lead to a lot of study in Africa and a lot of interest in what's going on in your country also, to try to better understand where we're heading. We may be seeing the beginning of the end of Artemisinins, which is a very important event in malaria.
Okay. If you permit, may I take one or two more questions?
Sure.
Yeah. So this is something related to nutrition. Does malnutrition affect the drug absorption and enhance the drug resistance?
I have colleagues who study this intensively, and I am often a collaborator on their studies, but I'm not the expert in this area. I don't think we have any convincing evidence that malnutrition has an important, there are some impacts of malnutrition on drug absorption, but whether they're important enough to lead to changing in dosing, for example, is something we continue to study, but I don't believe we have any data that's convincing so far. You may know that the dosing regimen for DHA piperacin in children was changed a few years ago. Young children were being somewhat underdosed, and so there are adjustments going on with good PK studies. And our collaborator in San Francisco, Fran Awika, has a really good lab that can do this, and there are a few other labs around the world that can do really nice PK studies. So we need to. I'm not really answering your question because I don't know of a clear evidence for that problem, but it's important to get a better understanding of it.
Okay, and similarly, one more question in hemoglobinopathies. Is there any role of hemoglobinopathies in ACT activities, specifically in high prevalent sickle cell population?
I don't know of a problem with drug efficacy with sickle cell. I wouldn't really anticipate a problem because their immune responses are normal and the parasites are still killed by the drug. So I would not anticipate that there would be a difference. Sickle cell impacts on drugs a little bit because there are still some parts of Africa where children are treated with chloroquine as prophylaxis when they have sickle cell, which is kind of a funny thing to do since there's so much chloroquine resistance, or at least there used to be. But so that's one reason chloroquine is still used in Africa. But in terms of it impacting on the efficacy of drugs, I don't know of a problem. Of course, as you all know, sickle cell trait offers some protection against severe malaria, but that's another story. But when people with sickle cell have malaria, to my knowledge, they do well with treatment.
Okay, so I would like to, maybe, is there any particular question? Yeah, I can take a very broad question. What could be the steps taken to combat malaria after seeing these resistance?
Well, we have multiple tools. We have really important vector control tools. They are challenged by insecticide resistance, of course, but there has been good progress recently. There's new insecticides and new combination insecticide or combination compounds in bed nets. In some of them insecticides, some of them have other ways of decreasing transmission. So those are really important tools. And, there are many malaria experts, including some on this call, I'm sure, who, when they think of malaria, are mainly thinking about the mosquitoes, not the parasites. And those tools are really important. But we also have to keep up with insecticide resistance. And of course, to be topical, we now have a vaccine. We could use a better vaccine. The R21 vaccine that was also published this year in the New England Journal showed considerably better efficacy than RTSS, though it's really the same antigen. So whether it's going to prove to really be better or not, we'll wait and see. It has a different adjuvant. It may truly be a better vaccine. And if it can give us the 75% preventive efficacy that was seen in the first study, that will be a big advance over RTSS. So we need a combination. We need We need good governance, lack of corruption, and all those things that allow you to do good public health. Unfortunately, the world has proven that this last 2 years with the pandemic, the world's proven that public health is difficult. Regardless of whether your country has a lot of money or not, it's difficult to have your population do the right thing. But in the case of malaria, we have a number of different tools, and we really need organized efforts to utilize them. I think we're doing a lot better than we were a few decades ago all over the world. More organized approaches, rational approaches to malaria control. But to be honest, in Africa, we're still not doing very well. We need to do better. And personally, it wouldn't be surprising to you, I'm particularly interested in better utilizing drugs. That's what I study. And I think we can do better. DHA proparaquine is one example of a drug that works well, but there are a number of different ways to utilize it. And there will be a number of others available in the coming years. New drugs that may be specifically developed for prevention rather than treatment. Medicines for Malaria Venture is increasingly thinking that way in terms of drug development. So vector control, drugs to treat and prevent malaria, and effective vaccines. That's what we need. And in terms of drug resistance, which was the basis of your question, obviously we need new drugs. And there's been a major effort for 20 years from Geneva and Medicines for Malaria Venture to develop new drugs, though it's mostly so far refined the drugs we've already had rather than develop completely new compounds. But those new compounds are coming. Okay, so with this answer, I would like to stop this session here. And if I'm sure if audience has any questions, they can directly write to Professor Philip. His email ID is on the screen. And this is for our audience. This was the third lecture in our distinguished lecture series. So we are running two simultaneously lecture series. This is the third lecture. The first lecture was from Professor Dave Stewart, then Professor Elizabeth Winsler, and now this is the third lecture. Next month we will have Professor David Sibley from University of Washington. So we are really thankful and grateful, and I really would like to thank you, Professor Rosenthal from NIMR, from Dr. Amit Sharma, from MERA-India team, that you spend your valuable time and you give us a very nice presentation. Well, thank you very much. I look forward to seeing you again. I was supposed to be in India at a meeting of the isomer groups, the United States Centers of Excellence groups. We were supposed to meet in Kerala. I guess it was in 2020. Of course, that did not happen. And look forward to getting back to India. I've had very nice experiences before. Absolutely. We would like to have you here in person. Please let me know whenever you are in India. Okay, great. Okay. Thank you so much. Everyone. It's been a pleasure talking to you. Bye-bye. Thanks. Bye-bye.